Our story begins billions of years ago, in the vast expanse of the cosmos. Imagine a vast cloud of gas and dust, stretching across light years of space. This cloud, known as a nebula, is cold and dark, a silent sentinel in the void. But within this seemingly lifeless cloud, a magnificent event is about to unfold, one that will change the course of our universe. Gravity, the invisible force that pulls objects together, begins to act on the nebula, drawing its particles closer. Slowly but surely, the cloud starts to collapse in on itself, a process that will take millions of years. As the cloud contracts, the material at its center becomes incredibly hot and dense, a cauldron of potential energy. Eventually, the temperature and pressure reach such extreme levels that nuclear fusion ignites, a cosmic firestorm. Hydrogen atoms begin to fuse together, releasing a tremendous amount of energy in the form of light and heat. Our sun is born. The birth of the sun marks a monumental turning point in the story of our solar system, a beacon of light in the darkness. It becomes the anchor around which everything else will revolve, the heart of our cosmic neighborhood, giving life and light to the planets that will soon form around it. The sun's birth was a dramatic event, a cataclysmic explosion of energy and light that marked the beginning of a new era in our solar system. But it wasn't the end of the story. Far from it. In fact, it was just the beginning of a much grander tale. The sun's formation left behind a swirling disk of gas and dust, a chaotic and dynamic environment teeming with potential. This disk, known as a protoplanetary disk, held within it the building blocks of our planets, the raw materials from which worlds would be born. Within this disk, tiny particles of dust began to collide and stick together, driven by the forces of gravity and motion. This process, called accretion, is like cosmic dust bunnies forming, a slow but steady accumulation of matter. Over millions of years, these dust bunnies grew larger and larger, eventually becoming planetesimals, the precursors to planets. These small bodies were the seeds from which the planets would grow. As these planetesimals orbited the sun, they continued to sweep up more and more material, growing ever larger and more complex. Some planetesimals even collided with each other, merging to form even more massive objects. These collisions were violent and transformative, shaping the future planets in profound ways. Through countless collisions and mergers, the planetesimals gradually coalesced into protoplanets, the early versions of the planets we know today. These young planets continued to evolve, their surfaces bombarded by leftover debris, their atmospheres forming and changing. Eventually, after millions of years of growth and change, the planets settled into the stable orbits we see today, each one a unique world born from the same swirling disk of gas and dust. The planets didn't just magically appear in their current orbits. Their paths were shaped by a delicate balance of forces, with gravity playing the leading role. Gravity is the force that attracts any two objects with mass. The more massive an object, the stronger its gravitational pull. The sun, being the most massive object in our solar system, exerts a powerful gravitational force on everything around it, including the planets. This gravitational pull is what keeps the planets in orbit around the sun. It's like an invisible tether preventing them from flying off into the vastness of space. Imagine swinging a ball on a string around your head. The string provides the inward pull that keeps the ball from flying away. Similarly, the sun's gravity provides the inward pull that keeps the planets in orbit. But why don't the planets just fall straight into the sun? The answer lies in their motion. The planets are constantly moving forward, perpendicular to the sun's gravitational pull. This forward motion, combined with the sun's inward pull, creates a curved path, an orbit. It's like a cosmic balancing act with gravity and forward motion working in tandem to keep the planets on track. Section 5. Oval Office, the elliptical path of planets. While we often visualize planetary orbits as perfect circles, in reality, they are slightly elliptical. This means they are more oval-shaped than perfectly round. The degree to which an orbit deviates from a perfect circle is called its eccentricity. Some planets have orbits that are nearly circular, while others have more elongated elliptical orbits. Earth's orbit, for example, is slightly elliptical, but it's close enough to a circle that we don't notice much difference in the amount of heat and light we receive from the sun throughout the year. Section 6. Rocky Beginnings. The inner planets. Not all planets are created equal. In our solar system, the inner planets, Mercury, Venus, Earth, and Mars, are rocky worlds. They formed closer to the Sun, where temperatures were too high for lighter elements like hydrogen and helium to condense. These rocky planets are composed primarily of heavier elements like iron, silicon, and oxygen. They have solid surfaces, making them suitable for things like volcanoes, mountains, and, in Earth's case, life as we know it. The inner planets are relatively small compared to the gas giants. Earth, the largest of the inner planets, is still dwarfed by the immense size of Jupiter and Saturn. Section 7. Gas giants, the outer solar system. Farther out in the solar system, beyond the asteroid belt, lie the gas giants, Jupiter, Saturn, Uranus, and Neptune. These colossal planets formed in the colder outer regions of the protoplanetary disk, where they were able to accrete vast amounts of hydrogen and helium. Unlike the rocky inner planets, gas giants don't have solid surfaces. They are primarily composed of gas and ice, with dense cores deep beneath their swirling atmospheres. Jupiter and Saturn, the largest of the gas giants, are truly enormous. Jupiter alone is more massive than all the other planets in our solar system combined. Section 8. Cosmic Ballet, the harmony of planetary motion. The planets in our solar system may seem like independent entities, but their movements are intricately connected. They all orbit the Sun in the same direction, and most of them rotate in the same direction as well. This harmony of motion is a testament to the way our solar system formed from a single rotating disk of gas and dust. The planets inherited their motion from this primordial disk, and they have maintained it for billions of years. The planets' orbits are not perfectly aligned, however. They are slightly tilted relative to each other, giving our solar system a dynamic and ever-changing appearance. Section 9. Our place in the cosmos, a perspective. Understanding how planets form and revolve around the Sun gives us a profound sense of our place in the cosmos. We live on a small, rocky planet orbiting an average star in a vast and ancient galaxy. Our solar system is just one of billions in the Milky Way, and the Milky Way is just one of billions of galaxies in the observable universe. The sheer scale of the cosmos is both humbling and awe-inspiring. Yet, despite our seemingly insignificant place in the grand scheme of things, we are a product of the same cosmic processes that gave rise to everything we see in the night sky. Section 10. Beyond our solar system, exoplanets and beyond. In recent decades, astronomers have discovered thousands of planets orbiting other stars. These exoplanets come in a stunning variety of sizes, compositions, and orbital configurations. Some exoplanets are gas giants that orbit incredibly close to their stars, while others are rocky worlds located in the habitable zones of their star systems, where conditions might be just right for liquid water, and perhaps even life, to exist. The discovery of exoplanets has revolutionized our understanding of planetary systems and has fueled the search for life beyond Earth. Section 11. The search for life. Are we alone? The question of whether we are alone in the universe is one of the most profound and enduring questions in science. For centuries, humans have gazed up at the night sky, wondering if there are other beings looking back at us from distant worlds. The vastness of the cosmos suggests that other life forms may exist, but we have yet to find definitive evidence. With billions of stars in our galaxy alone, and countless galaxies beyond, the potential for life elsewhere seems almost inevitable. The search for extraterrestrial life is a daunting task, but it is one that continues to inspire scientists and capture the imaginations of people around the world. From analyzing the atmospheres of distant exoplanets to studying the extreme environments on Earth where life thrives, researchers are leaving no stone unturned. The discovery of even a single microbe on another planet would be a monumental event, fundamentally changing our understanding of life in the universe. It would suggest that life is not unique to Earth and could potentially be common throughout the cosmos. As we continue to explore the cosmos and unravel the mysteries of the universe, the search for life beyond Earth will undoubtedly remain a driving force in scientific exploration for generations to come. The quest to answer the question, "Are we alone?" pushes the boundaries of our knowledge and fuels our curiosity, reminding us of the infinite possibilities that lie beyond our home planet.